away from us. Now this leads us to the 4 ages of astronomy. Up until Galileo, all observations were done with the naked eye only. So the ancients, the Greeks, Kepler, Tycho Brahe, all did their observations with the naked eye. And once the telescope started to be used, a new era of discovery of nebulae, of galaxies, and other celestial objects began. That's the second age, the simple telescope. The third age is photography and spectroscopy. So from Galileo to World War II, the telescope was used by viewing through it. So beginning around World War II, photographic cameras were beginning to replace the eyepiece in telescopes. So by exposing for long amounts of time, new objects were observed in the sky that were too faint to be seen by eye, even with a telescope. The fourth age is more recent, where we've started to look at the sky in other electromagnetic spectra. So other instruments begin to be used, instead of just a camera, to observe the sky in all electromagnetic spectrums. So what's the future? Probably going to be dominated by things like automated surveys. I look at the sky, I look at the same sky again a little bit later, I look for slight changes, and be able to determine how things are changing in time. And we need to understand a telescope a bit. So the first thing we need to understand is a lens. A lens is a curved bit of glass that bends light rays to a point called the focal point of the lens. And it happens because light travels slower in gas than in air. So as it goes across the surface, and the part that hits first slows down first, and it actually causes it to bend, and we can get the light then to focus down on a point. The first telescopes were refracting telescopes. They consist of 2 lenses, an eyepiece, and an objective lens. The objective lens is what focuses the light down from whatever I'm looking at, and the eyepiece changes it so that it focuses correctly on your retina in your eye. Now this was the design of Galileo's telescope. However, his was very small. There's some problems with refracting telescopes. The first is they're usually very long tubes that are hard to keep stable. But more importantly, they're susceptible to chromatic aberration. Different wavelengths of light bend slightly more or others, and it usually depends on the wavelength. So the speed of light in glass depends on the wavelength of the light. So in this case, white light comes, the violet light is going to focus at a slightly different place than the green and the red. And so no matter how I'm looking at it, if I get the green light in focus, the violet and the red will be slightly out of focus. So telescopes improved dramatically with the invention of the reflecting telescope. It uses an eyepiece lens and a mirror. The first reflectors used spherical mirrors, but they didn't focus well due to a phenomenon called spherical aberration. That light that strikes different parts of the mirror all crosses at the same time. It doesn't matter what color it is, it'll focus here, but different places focus at different locations. Therefore, I get, again, a blurriness due to the spherical nature. Now, if I make my mirror in the shape of a parabola, the parallel light rays all strike at the same point, and I don't have any aberration. So good reflecting telescopes have a parabolic mirror. There are several kinds of reflectors. The first was invented by Newton, and it's called a Newtonian reflector. It has an eyepiece along the tube, a small mirror at 45 degrees, takes and bends the light out here, so the light comes in, strikes the objective mirror, that causes it to come into focus out here, but this mirror bounces it back to focus here. And as it goes through the focus, the eyepiece refocuses it on the eye of whoever's looking at it. Another type is called the Cassegrain telescope. It has a second curved mirror that focuses the light through a small hole in the back of the objective mirror, so that the eyepiece is opposite the opening that you're looking through. This is the type that's most available today. In general, the bigger the mirror, the better the telescope. But big mirrors are very hard to make. Until recently, with laser optics and modern machining technology, the telescopes are very expensive. A bit of word of advice. If you decide to delve into amateur astronomy at some point, are going to buy a telescope for a friend or family member, remember this. Don't waste your money on a cheap refractor. This is the $99 telescope at Walmart or in different other places. They're hard to use and are generally more frustrating than enjoyable. Good reflectors are not that much more expensive and are well worth the money. A good reflecting 5-inch reflecting telescope might only cost you a couple $100. A good telescope today no longer needs a special mount, but has a computer-controlled movement that most of the visible objects are programmed in, so you don't have to read up and try to figure out where things are. You can just enjoy looking at the stars. Now, modern professional astronomers no longer do any optical viewing. Very few eyeballs go up against telescopes. Modern telescope has a camera, which is for the most part is electronic. More than half of all observations by professional astronomers are spectroscopy, so looking at the parts of the spectrum that are emitted by various celestial objects, not even trying to form an image, just looking at what different wavelengths of light come off the object. Now, one of the problems with looking at the stars is we're on the Earth, and it tends to move. So, with the Earth rotating, one had to constantly keep moving your telescope to keep the object you wanted in view in the field of view, or the area of the sky your telescope could see. All sorts of mounts were designed to aid this process. This is actually Newton's telescope, and he had a little wooden ball that it sat on, and literally you would have to keep the object you're looking at in the telescope by moving it with your hands all night. Now, there was an invention called the equatorial mount, and it allowed an astronomer to keep the telescope pointed in one place for a long period of time. Essentially, you took your telescope, you took the axis of your mount and it pointed towards the North Pole, and then you put a clock on it, and so that the axis turned at the same rate as the Earth turned, and that way, even if you're looking off at a different direction, the telescope would be turning and would always match the rotation of the Earth. A properly aligned telescope with an equatorial mount can hold a star in its field of view all night long. And the other thing we have to consider with telescopes is where we are going to set up our observatory. For best viewing, you need a clear, dark, dry, smooth air sky. Professional telescopes tend to be built in low latitudes so that more of the sky is visible at any time. So international cooperation for major telescopes is a must today, and many of the big telescopes are actually owned by several countries. Now, radio telescopes are used by professional astronomers and look nothing like optical telescopes, but use the same principles. We have this large reflector here, which acts like the mirror at the back, but it reflects radio waves, not light waves. And the eyepiece instead is some instrumentation at the focal point. This is pictures taken at the National Radio Observatory in Green Bank, West Virginia. This radio telescope is 480 feet across. You can see the semi-truck down here. It gives you an idea of how big this radio telescope is. Now, if I want to look at infrared light, we have flying aircraft high in the atmosphere, and it can observe the infrared regions of light spectrum. The telescope generally has to be cooled with liquid nitrogen, so minus 320 degrees Fahrenheit. All objects emit infrared light, even the telescope, so we have to cool it down so that it's dark, and we can see the infrared and not have the infrared being given off by the telescope body itself change what we're looking at. Of course, we also have telescopes in space. The most famous is the Hubble Space Telescope. And it was built to avoid the atmosphere, but today we can actually do a little bit better with the invention of adaptive optics. However, it's still the best way to observe in the ultraviolet region of the spectrum. Generally, atoms have lots more transitions in UV than the visible, so therefore it gives us some idea of which atoms are present in the object being viewed. The science of understanding what elements are present from the light emitted is spectroscopy. Space telescopes are the best for infrared, for ultraviolet, for X-ray and gamma ray light regions. And this is the end of Chapter 4.